Last class, what we did is we looked at the graphs of sine, cosine, and tangent, and we talked about their attributes, and we started to highlight the different things that can be transformed on those graphs. We're going to do the same thing today for the reciprocal functions. And since secant, cosecant, and cotangent are all reciprocal of sine, cosine, and tangent, their graphs will also be reciprocals of these basic trig functions. So anytime I graph a cosecant, secant, or cotangent graph, I like to actually start with having the sine, cosine, or tangent function graphed beforehand so that I can use the amplitude, the period, midline, and phase shift to correctly graph those particular functions. So the first graph that you cut and paste hopefully was the cosecant function. In our table this time, I already have the angles and I have sine listed for you. Cosecant is the reciprocal of sine. So I want to take the reciprocal of all of these values. First things first, what is the reciprocal of 0? 0 is like 0 over 1. Undefined, because it'd be 1 over 0, correct? So this first thing that's happening is going to end up being, why does that look so funky? It's end up going to be a vertical asymptote. What is the reciprocal of 1/2? 2. What's the reciprocal of 1? 1. What's the reciprocal of 1/2? Reciprocal of 0? Undefined. What's the reciprocal of negative 1/2? How about negative 1? Still negative 1. And what's the reciprocal of negative 1/2? And then we have an undefined again. So, all right, we need to figure out what this might look like. And again, having the sine function graphed in between would be very helpful. First thing I'm going to start with is graphing those undefined vertical asymptotes. So we have the values here, boom, 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 where my vertical asymptotes would be, which is at 0, at pi, and at 2 pi. What do you notice is happening in the sine function at 0, pi, and 2 pi? Well, that's in the cosecant function. In the sine function that's graphed here on your page, what are those called? The zeros of the function. So anywhere the sine function has a 0, the cosecant function is going to have a vertical asymptote. Okay, cool. Let's plot the other points. We have the coordinate point pi over 6, comma 2. We have the coordinate point pi over 2, comma 1. And the coordinate point 5 over 6, comma 2. Then we jump to the next bowl, and we have negative 7 pi over 6, 7 pi over 6, comma negative 2, 3 pi over 2, comma negative 1, and 11 pi over 6, comma negative 2. If I play connect the dots here, the cosecant function is the reciprocal or the flipped version of the wave that creates the sine function. The sine function is not a part of this. That's why it's dashed, right? But the reciprocal of it, I like to call them bowls. I don't think that's a really correct math phrase, but if you take the sine function and you flip it, those makes bowls that are going up and down instead of connecting together. That's what it looks like to me. Now, obviously, this would continue on and on. So if we were actually going on this side as well, we'd have another bowl coming up like this. And if the graph kept going, we'd have another bowl that goes like this. This is the cosecant function. Let's talk about the domain range zeros and the properties of the, cosecant function. Is the domain of this function all real numbers? Are there any places where this graph is broken? Yeah, there's plenty of places where the graph is broken. So to answer the domain question, we'd say it's all real numbers except for the places where those vertical asymptotes are. The equation for the vertical asymptotes here are x equal to 0 and every pi after that, because that's how long it takes for me to find another 0 of the sine function. Now, the range of the sine function was between negative 1 and 1 because that was like in between here, yes? The cosecant function is literally everything except for negative 1 and 1. So when we answer the range, we'd say that this range goes from negative infinity to negative 1 or 1 to infinity because it's everything except for things between -1 and 1, since it's the reciprocal of the sine function. Looking specifically at the cosecant, so ignore the dashed line for sine, looking only at the actual cosecant graph. What are the zeros of the cosecant graph? Does this curve ever actually touch the x-axis? No, so the cosecant function has no zeros at all. It does, however, have vertical asymptotes, which we already wrote the equation for earlier. These vertical asymptotes appear at x equal to 0 and every repeat of pi after that. So we have a general equation for the vertical asymptote. If your graph has different vertical asymptotes, it probably has been shifted from side to side. Much like sine, since cosecant is a reciprocal of sine, cosecant is an odd function. And if we remember, odd means rotational symmetry about the origin, and it also tells us that if we plug in a negative number to cosecant, we should get out the opposite output value of cosecant. Odd, origin, opposite. Odd, origin, opposite. Last class, we also had 4 colors that we annotated our graphs with to discuss the different ways we can transform them. Let's add those 4 colors here. In our graph, cosecant technically does not have amplitude the way that sine and cosine does. But do you see how in the same way that the number that would change the amplitude for sine shows me where that lowest and highest relative min and maximum is for the bowls of cosecant? That's still going to be the a value in a transformation of this function. The midline, or the displacement, is still the average between those relative maxes and mins. And again, it comes from the sine function that this is based off of, which is why we're able to connect the transformations from one type of function to the other. The period of the cosecant function, like sine, is 2 pi. So it takes me from 0 to 2 pi to complete an entire period of this function. Basically, I need an upward facing bowl and a downward facing bowl to complete the entire shape before I start to repeat. And this is kind of funky to do, so we're going to do it in a weird way. The starting point here is a vertical asymptote. So we don't actually have a phase shift number to highlight the way we did in our other graphs, because this graph should start with a vertical asymptote. And if yours does not, that means it has been shifted from side to side, and you'd have to change the phase shift to account for that. So we don't have a green highlighted part, we just have a vertical asymptote to highlight. So for the parent function of the cosecant graph, again, it's not the amplitude because it doesn't have an absolute max and min, but we can think of the amplitude as the number that it takes for me to get to the relative min and max of the bowls, or the actual amplitude of the sine function that creates this. The period of this function is 2 pi. It uses the same formula to find b as sine does, since it's related to that graph. So we know that the b value here is 1, since 2 pi divided by 1 is 2 pi. For the parent function, again, we don't have a phase shift for this graph because it's the parent function, but what we learned is that the graph should start at a vertical asymptote, and the first bowl should be upward facing, and then downward facing, and upward facing, and then downward facing. And then last but not least, for this graph, the midline, which would be halfway between the relative maxes and mins, should be at 0. And if your graph has been shifted up or down, the value that would be added or subtracted to your function will be different. So all of the transformations from sine, cosine, and tangent are the same for secant, cosecant, and cotangent. So we're going to see this color scheme over and over again. Again, today in the notes, we're just getting the basic parent function, and then you'll have to transform them on your own. When we look at secant, We know that secant is the reciprocal of cosine. So again, we're going to take the table of values for cosine around our unit circle from 0 and 2 pi. We're going to find the values for secant. This time, cosine of 0 was 1. What is the reciprocal of 1? 1. What is the reciprocal of 1/2? 2. And the reciprocal of 0? Undefined. If I keep going and continue to do the reciprocals of all of these values of cosine around the unit circle, I'd end up with the following table. How many vertical asymptotes am I going to draw for this graph between 0 and 2 pi? 2 of them, because I have 2 places where my graph would be undefined. These occur at pi over 2 and at 3 pi over 2. Again, what do you notice is happening this time in the cosine function whenever I drew these vertical asymptotes? Whenever it crosses the x-axis, which is called a 0, correct. So we have the zeros of the function of cosine creating vertical asymptotes in the graph of secant. Once we do that and we start plotting our points to play connect the dots, we end up with 0, 1, pi over 3, 2, 2 pi over 3, -2, pi, -1, 4 pi over 3, -2, 5 pi over 3, +2, and 2 pi, 1. When we play connect the dots, again, it's like each of the bowls that create the sine wave, sorry, this is cosine, the cosine wave get flipped over. Obviously, this one would continue up this direction if I kept graphing it, and vice versa. All right, let's add our colors to this graph as well. And I will say, if you're like, man, I can't tell the difference in my handwriting, make these really bold. Okay, this is actually the graph of secant. The dashed line in between is just showing you how it relates to cosine. It's not a part of the actual function. It just would have all these bowls going up and down. For this function, the displacement or the midline is still in the middle of the cosine function that creates it. So my midline is still at 0. And it is still the middle of the relative max and mins of each of the bowls. And much like sine, the amplitude of the cosine function will give me the amplitude, quote, amplitude of the secant function. It'll tell me how high the lowest minimum is and how low the lowest maximum is. This one we do have a phase shift number. So if we're looking at the phase shift, we can actually plot a point for my y-axis. This one doesn't start with a vertical asymptote. It starts with one of those relative minimums. So if your graph is a secant graph and it doesn't start at one of those relative minimums, it might have been shifted from side to side. And the last color we add here is for the period of the function. Because it's based on cosine and cosine has a period of 2 pi, secant also has a period of 2 pi. So if we go list out all of the basic information, oh, I didn't write down any of this basic information, did I? I got ahead of myself. Let's talk about the domain and range and all that good stuff, then we'll go back to the colors. So sorry. The domain of this function is not all real numbers because I know that we have vertical asymptotes. So we would say that it is all real numbers except the general equation for where I see the first vertical asymptote and every repetition of pi after that. Every single time I get to a vertical asymptote. Since this is the reciprocal of cosine, the range is also the reciprocal, meaning it's everything except for -1 to 1. So from -infinity to -1 or 1 to infinity. This graph has no zeros because, again, it does not cross the x-axis. It is outside, right? It is the flipped version of cosine, so it doesn't cross the x-axis at all. But it does have a nice equation for the vertical asymptotes, which we already wrote in the domain. The vertical asymptotes appear at x equal to pi over 2 and every pi afterwards. If yours don't, that means it has probably either been shifted side to side or the frequency has changed. Because cosine is an even function, secant is also an even function. An even function is the one I can fold along the y-axis, and I also know that secant of a negative angle will be equal to the regular angle itself. Even is y-axis and the same. Odd, opposite origin, even, y-axis, the same. Again, if we look at the color scheme type of values, secant doesn't have an amplitude, but we know that the number works like an amplitude. So if I vertically stretch or shrink this graph, it's going to change where those relative maxes and mins for those bowls are. So if yours has moved up or down or like stretched away or towards each other, your amplitude, quote, has changed the a value. The period of this function is still 2 pi. Which means for us that the b value is equal to 1, because 2 pi divided by 1 is 2 pi. The phase shift for the parent function is obviously 0, but if your graph does not start in the same sort of place, meaning we want it to start at a relative minimum, and then increase. We're starting in the middle of a bowl and then finishing increasing. And if yours doesn't, it probably has been moved from side to side, and we would need to adjust for that. And last but not least, the midline is still 0 for this function. If your graph has been shifted entirely up or down, you will need to adjust the number that is being added or subtracted to the function. So yeah, the phase shift, going back to this, it says start at a relative minimum and then increase. So what I mean by that is this is a relative minimum of this bowl. So we have to start in essentially the middle of the upward facing bowl and continue. Great question, thank you. This next graph is going to get a little messy, so this is where I really, recommend that you make your lines for cotangent pretty bold. Because what we're going to do is we're going to take all the values of tangent and do the reciprocals. And if we remember when we did tangent the other day, we have these S-curves for the tangents. In between them, we had a whole bunch of vertical asymptotes. I didn't draw the vertical asymptotes for you because it really would get messy. But let's get started. Tangent of 0 is 0, which means the cotangent of 0 is... What's the reciprocal of 0? Undefined. All right, so then we go through this entire graph and we do the reciprocals. The reciprocal of 1 is 1. Whoa, but then we're doing the reciprocal of undefined. It would be 0. Very good. The reciprocal of -1 is -1, and then an undefined moment, and then +1, and then 0, and then -1, and then undefined again. So I see that there are going to be 3 vertical asymptotes that I'm going to graph between 0 and 2 pi. I'm going to have a vertical asymptote at 0. I'm going to have a vertical asymptote at pi. And I'm going to have a vertical asymptote at 2 pi. Just like the other functions, the places where I have the vertical asymptotes are where the zeros of its reciprocal are occurring, since 0 and undefined are reciprocal numbers. And if I start to plot points, I would go to pi over 4. Ooh, it's not on here, is it? Is pi over 4 on y'all's? No. Okay, so pi over 4 is between pi over 6 and pi over 3. Just do your best. So we're going to have a 1 right here. Pi over 2, comma 0. And 3 pi over 4, comma -1. Again, between the 3 and the 6 fraction. Then I have my undefined value. And then I have 5 pi over 4 comma 1, 3 pi over 2 comma 0, and 7 pi over 4 in the middle, comma negative 1. What do you notice about these coordinate points, specifically the ones that I didn't give you an over 4 fraction to look at? What are they? How are they related to tangent? They're like on an actual spot for tangent, correct? It's very interesting. When we go to play connect the dots, this is the one I want you to make pretty bold on your paper, or else you're going to get a little bit confused. And if we graph this, bless you, we now have, instead of a continually increasing graph, tangent was always increasing, cotangent is going to be a decreasing graph. I'll give you a moment to make this one pretty dark, so I do want you to like bold this line for yourself. So again, I notice now that not only do I have vertical asymptotes where tangent was 0, I have zeros at the places where tangent had a vertical asymptote. I also, instead of having an increasing function like I do for tangent, have a decreasing function for cotangent. Very interesting. Let's talk about the attributes of this function and then we'll start color coding. The domain of this function is not all real numbers. Because we have these vertical asymptotes, we'd say its domain is all real numbers except for the places where I find those vertical asymptotes, which would be at x equal to 0 and every pi repetition after that. The range of this function, though, is unchanged. I'm still going from the very, very bottom of my number line to the very, very top, which means my range is all real numbers from negative infinity to infinity. Bless you. Does this graph have places where it's going to cross the x-axis? Yeah, we actually do cross the x-axis here and here. Hopefully you didn't make it too bold. You can't see that number. What number is this? Pi over 2. What's the next one? 3 pi over 2. So my zeros for this function typically occur at x equal to pi over 2 and every repetition after that. This graph does have vertical asymptotes like the other reciprocal function, so we can give it an equation. The vertical asymptotes is x equal to 0 plus pi k, so at 0 and every repetition of pi after that. 1 pi, 2 pi, 3 pi, 4 pi, on and on. Because tangent is an odd function, it also makes cotangent an odd function, which means we have rotational symmetry about the origin, and that cotangent of negative x would be the same thing as negative cotangent of x. That I can put in negative input value and get the opposite output value. That's the definition of rotational symmetry or odd functions. If we start to add our color scheme like before, we can start with the midline. The midline is going to be where this graph has those points of inflection. So for the parent function, it's at 0, like everything else. The fake amplitudes, just like with tangent, occur that show me where the important points are for graphing the little S-curve that creates cotangent. If yours stretches up to 3 and negative 3, that means you have changed the fake amplitude or the A value in that transformed graph. Like sine, this graph starts with a vertical asymptote. So if your cotangent graph does not start with a vertical asymptote, that means it probably has been shifted from side to side, and we need to account for that as a phase shift. And then last but not least, the period of cotangent, like the period of tangent, is simply just pi. That's how long it takes for me to finish an entire S-curve for this cotangent function. So if we write down all the info like we've done for everybody else. Yes? 1 second, yeah. The amplitude is 1 because that's how tall the vertical stretch or shrink is for this cotangent function. You got it? Okay. The period of this function, like tangent, is just pi, which for us means that b is equal to 1, since pi divided by 1 is pi. If your period of your function is different, that means you have done some sort of horizontal transdilation. The phase shift for the parent function is 0, obviously, because it's the one we're comparing it to. But we know that cotangent starts, that's not how you spell the word starts at a vertical asymptote and decreases. The midline of all basic cotangent functions, like tangent, is at 0. So if your graph has been entirely shifted up and down, that would be a vertical translation, and we would change the number that is added and subtracted to the function. So again, last class we covered sine, cosine, and tangent and how to transform those graphs. Today we talked about their reciprocals, cosecant, secant, and cotangent, and what it might take for us to transform those graphs. There were no examples in the notes, which means all of your examples and learning will come from your homework. So we're going to spend the rest of the class period working on our homework assignment. If you wanted to go back and finish 4.1 through 4.3 first, which is sine and cosine, I would actually recommend doing that so we have the basics of the 3 basic trig functions before we get into the reciprocals. It would be helpful.